Good morning, everyone. Welcome to our second AP Statistics Content Review session. Today's topics are experimental design and probability. We have our presenter today, Dan Kemp, and he is from Louisville Middle High School in Louisville, Kentucky. And while this is an online review session, it's intended for a Kentucky audience. Then, space permitting, we welcome students from all over the country and some in other parts of the world. And we will do all that we can to provide every student with an equitable opportunity to learn. So during this session, we're going to encourage participation, but please know that any participant causing a disruption will be removed. AP is a trademark registered by College Board, and it's not affiliated with and does not endorse this product. I am Dr. Sherry McGuffin. I'm STEM coordinator for Advanced Kentucky. I'll be your host today, and if you have anything that you want to add in the chat, I'll be monitoring the chat as well and I'll be directing questions to him as well as myself. And Dan and I have both been AP readers, and so we've had lots of different experience with free responses and scoring all of those free responses during the summer. So I'm more than glad to have every one of you today. Please put any questions that you may have in the chat. And just a little bit of etiquette here. Number one, first of all, with microphones, all your participants will be, their microphones are muted upon your entry. Please leave your microphone off unless you're otherwise asked. Video is also going to have your, that is going to be off upon entry, and just please leave your video off unless otherwise asked. It really helps with bandwidth to keep the videos off. But please, please, please participate in the chat at the bottom of your Zoom screen, or if it's on your phone, you click the three dots and you can ask the chat as well. And we'll be monitoring that chat, so ask away. So the recordings of the link for the recording today will be accessible at bit.ly at Advanced KY at the link that you see on the screen, and I'll be posting that to the chat as well. We have upcoming events. This is just the second of a number of study sessions and content review sessions that are going to be offered by Advanced Kentucky. And if you go to that bit.ly link, click Math and Computer Science at the top, you can see the schedule and the presenters and the timeline for all of those. And with that being, we'll stop sharing my screen and start, I guess, monitoring those that are coming in, because they're coming in by leaps and bounds now. I will turn the microphone over to Mr. Kim. I'll have him introduce himself and take it away.
Thank you so much, and good morning to everyone. I'm going to drop off a link in the chat box right now. And if you would click on that, today we will go through a couple of Desmos activity. If you're not familiar, that's perfectly fine. If you are, then hopefully you will know what to do here. I will also start sharing my screen. The instructions will be on this share screen as well. So here we go. There it is. So you can either click on the link that I just put in the chat box, or you can go to student.desmos.com and type in TQ4ZD4, as you see on the screen. And I will continue to share the screen. So my suggestion is, depending on your monitor size and situation, you can focus on the Desmos screen that you'll be working on. My goal is for you to just participate and interact and just really, dig into some of these questions instead of just, hearing me talk and watching the video today. Dr. McGuffin said, if you have any questions, please don't hesitate and chime in. If we don't get through all these questions, that's fine. Let's really try to dig into some of these questions this morning. And lastly, your name has been anonymized. All of you guys will be famous mathematician this morning. Your responses, if I do decide to share them on my screen, nobody will know that it's from you. Just ask that you please keep it appropriate. So I see that 15 people have joined so far. I'll give you guys about a minute more. And also, you will be paced. you'll see right now that you cannot go beyond slide number 1 right now. And what I'll do is I'll just continue to open up slides. You have access to all the previous slides, but I'm going to try to pace us so that we can kind of move on together. Okay, so I see 18 people joined in. So again, if you're just joining us, please go to student.desmos.com and type in TQ4ZD4.
And I do have that in the chat as well. So if you need it, it is there for reference.
Okay, so I'm going to close this box here. Again, I'm Mr. Kim. This is my 16th year of teaching. I've been teaching AP Stats for nine years and served as an AP reader. So hopefully between Dr. McGuffin and I, we can offer you guys and hopefully answer a lot of your questions that you may have about the AP exam specifically today. So guys, let me go ahead and give you guys access to slide number 2. You don't have to give me an essay answer, but I wanted to just start this morning with a quick warm-up. It's a simple agree or disagree question. There's a slider that you can move up and down, and just maybe in a sentence or two, how would you answer this question? Would you agree or disagree with the statement? AP Stats is a math class.
I was looking at all those mathematicians there. I don't recognize some of their names, Mr. Kim. Well done.
There are some famous people in this room right now. Famous people. Let me see if I can recognize one. Henry Poincaré, you're one of my favorite mathematicians. So your response is you still use some basic algebra, but it does go farther than that, just that. It also involves critical thinking. And overall, I just want to show you guys overall here. So nobody's disagreed with the statement. All 18 of you said you either moderately agree to strongly agree. That's interesting. So the reason why I asked this question this morning is because the goal of this session is the 3rd unit of AP Statistics, which is about collecting data. And that sounds like numerical, that sounds mathy. But if you think back to this unit that you guys studied, I don't know how many months ago, weeks ago, there was hardly any math, like what you and I would call math in here. So my suggestion to you is if you didn't quite like this unit, if you didn't like this chapter, it's chapter 4, if you're using the practice statistics, I would just encourage you guys to just kind of, give it a second thought, give it a second chance and say, okay, maybe this doesn't have to be this overly mathy kind of a thing, maybe I need to be maybe I just need to expect myself to writing more words than numbers. And then, of course, I just said this, and about an hour from now, we're going to review the probability unit, which is totally more mathy than this. So AP Stats is just a nice combination of math, science, English, all of it just all lumped in together. So thank you for your responses. That was fun. Let's go ahead and go on to slide number 3. So slide number 3, I just want to quickly show you here what do I mean by unit 3, and it's called collecting data. And notice here it says it will account for 12 to 15% of the AP exam. So this single unit, the single chapter from a lot of our textbook is going to account for at least 12% of the AP exam. So I don't think 50 minutes is quite enough, honestly, to review every single details. But I also don't want to bore you guys with every little detail about this chapter. So my goal is to work through as many problems as possible and try to, I guess I'll give my 2 cents on here are some must-have skills. If you have to know this going into the exam. So let's go on to slide number 4 here. So must-have number 1 is this term bias, and it is one of the most misused words in AP Stats, period. I think we throw around this 4-letter B word a lot, and I would argue, unfortunately, a lot of the times, teachers and students alike, we tend to misuse this word. So here's the definition of bias, just for our review sakes. The design of a statistical study shows bias if it is very likely to either underestimate or very likely to overestimate the value you want to know. And so the AP exam tip that I would offer you today is that when you're asked to describe how the design of a sample survey may lead to bias, you have to do 2 things. Number 1, you got to describe in context, of course, it's all about the context, how the individuals in the sample may respond differently from the rest of the population. And number 2, explain, again in context, how this difference would lead to either an underestimate or overestimate. In other words, like, avoid vague response like, this is going to lead to bias, period. It's not going to really get you anything. So let me actually give you a chance to practice this. Slide number 5. This is an actual FRQ from 2013. Let's read the problem together. So step of the question says, an administrator at a large university wants to conduct a survey to estimate the proportion of students who are satisfied with the appearance of the university buildings and grounds. The administrator is considering 3 methods of obtaining sample of 500 students from the 70,000 students at the university. And here's part A of this question. Because of financial constraints, the first method the administrator is considering consists of taking a convenience sample to keep the expenses low. A very large number of students will attend the first football game of the season, and the first 500 students who enter the football stadium could be used as a sample. Why might such a sampling method be biased in producing an estimate of the proportion of students who are satisfied with the appearance of the buildings and grounds? So I want to give you, and I'll try to time you guys so we don't spend too much time here. I want to give you guys about 2 minutes to try to answer this question to the best of your ability.
Dan, how many students do you have in your class now? How many do you see there? I have a couple of people that are working on joining still, so.
Okay. Okay, so that's about 2 minutes right there. And obviously, on the actual exam, you would have much more time than this. And also, just for you to consider, and I'll just briefly mention this without really getting into it, there's going to be options for you this at the end of the school year, right? There's going to be an option for you to take a sit-down paper pencil version of this test, or you can actually have the option of taking it on the computer. So something for you to consider, like most of us can type faster than handwrite. So on a question like this, if you've been used to, online learning throughout the school year, like my classroom, my students have never set foot in the building so far this school year. So they're very used to typing fast, and that's a plus because it allows you to express your ideas with more words. However, something for consider is sometimes on a question like this, is not necessarily like how much you say. It's really about like, are you saying the right things? Are you really addressing the question here? So I'm looking at really good responses. What I want you guys to do right now, take a look at the model solution. It is longer, I'll tell you that. This is a model solution from the College Board on slide number 6. But what I did for you there is like, what are the absolute things that you actually have to have in your response to get full credit here? And those are bolded here. So for instance, the 500 students, they probably have more school pride. They're the first to show up to the football game. So there's a difference right there. A lot of you guys were saying like, these 500 students are not necessarily going to be a true representation of the entire 70,000 students. And there's a reason why. They probably have more school pride. So how does that lead to bias? So going back to the definition of bias, systematically overestimating or systematically underestimating some population truth, that's the next bolded part here. So perhaps the school pride is related to having more positive opinions about the university buildings and grounds. In which case, the sample proportion, the percentage of students in this sample who are satisfied would probably be higher than the general. So they're going to overestimate. So for instance, like you find that 90% of them say, oh yeah, like we love our campus. We think it's beautiful. That 90% is likely higher than the true percentage of students throughout the university who may have that sentiment. So I'll give you guys just about 30 seconds to go back and forth if you will. If you want to, take a look at your response. And I'm not asking you to like put a guilt trip on you. Just consider like if this was the standard for being graded, aka essentially correct, and I wonder if your teacher has talked about this grading yet, this is what it takes. It takes both of these components to earn an essentially correct response, and one of these two will get you essentially half credit called partially correct.
Dan, there was a comment here and a question. And could you go the other way and say they have higher standards and want the university to improve the buildings?
Absolutely. Yeah, this is one model solution. That's a great point. So in this case, yeah, you can make, as long as you logically make your argument, you can get full credit. It doesn't have to be exactly this. Okay, so let's take a look at must-have number 2. Must-have number 2 from this unit is you absolutely have to know how to describe random selection in a sampling, environment scenario, or random assignment. Like here's you're going to do an experiment. How would you now randomly assign your subjects or the experimental units to the treatment groups? So the big idea here is you absolutely have to know how to describe how you would choose a random sample or how you would randomly assign subjects into treatment groups. And your description has to be, this is what I tell my students, has to be clear, has to be correct, and it has to be fully replicable by another knowledgeable user of statistics. So imagine writing a letter to a friend who's taking AP stats with you. Can they read your response? Can they read your description and actually be able to conduct the sampling mechanism or the experimental mechanism that you just described? So the example that I have for you is you should be familiar with both of the HAT method and the technology method. And honestly, in my opinion, is the table D method that's a lot of in our books. I think is outdated, quite honestly, and I think is inefficient. So let's focus on the 2 methods. The technology method, the 3 steps. First, you want to label. You want to give each person in the population, the sampling frame, a unique label. So if there are 500 people, you might want to label them number 1 through 500, if you will. And then you're going to use a random number generator. You can talk about rand int feature on your calculator, or you can just simply say, I'm going to use a random number generator to obtain the sample size that I want. Maybe I want to choose 50 subjects out of 500 people. So now I'm going to randomly choose 50, and get this, you got to mention this word, 50 unique numbers. Like, so this is without replacement. Once you, let's say, pick person number 40 to 50 out, you don't want to put number 450 back into the pool. So if number 450 comes up again, it's like, okay, that person's already been chosen, so I got to keep doing 50 unique numbers. And then step number 3 is simply to talk about, okay, you know, the individuals that correspond to the numbers are going to be selected. That's the technology method. The hat method is actually my personal favorite. It looks really similar. So instead of using technology, this is like, okay, let me go the old school route, paper, pencil, on identical slips of paper, write the names, or maybe, you know, the numbers for each individual. Then now the randomization part here is not a random number generator. Step 2 here is, so you can put the slips of paper into a hat, shake it really well, you know, shuffle it around, and then you can draw out however many slips of paper, again, without replacement. That language needs to be in there. And of course, those people drawn out will be in your sample. So take a look at part B of this question. I'm not going to read the STEM again, but take a look at part B. So because of a large number of students at the university, the second method the administrator is considering consists of using a computer with a random number generator to select a simple random sample of 500 students from a list of 70,000 student names. Describe how to implement such a method. Again, I'll give you a couple of minutes to try to answer this question. Okay, lots of great responses. So again, I wish I could give you more time. Hopefully 2 minutes was at least enough for you to start thinking about this question at least and put in some response. So continue to finish if you wish, if you want to, but I'm going to give you access to the next slide, which has a model solution. So the model solution says obtain a list of all 70,000 students. Assign an ID number from 1 to 70,000 to each student. Some of you guys talked about how, you know, you can use student IDs. Just throw them into the random number generator, and you can do that. Then use a computer to generate 500 random integers between 1 and 70,000, and there's that verbiage, without replacement. Without replacement meaning like I want 500 unique numbers. Like I can't select the same person twice. And then the student whose ID number corresponds to those numbers will be in the sample. Now, again, my favorite method is the hat method. And even though the question did say, like, yeah, there's 70,000 people, do you really want to throw 70,000 slips of paper into this gigantic hat? Probably not. But, you know, some of my students, you know, over the years, they purely rely on this old school method of using the hat. And so it can be answered that way. So I'm providing you what I would have written down if I were a student and I want to say, you know what, I'm going to use my HAT method. On identical slips of paper, write the ID numbers from 1 to 70,000, tedious task, right, for each student at the university. Place the slips of paper in a pretty large hat, shake well or stir well, and now draw 500 slips at random without replacement. And the students whose ID numbers were drawn will be in the sample. So I really think that this is an absolute must-have skill from this unit, whether it be in a sampling situation or whether it be like here are 30 subjects, you want to assign them at random into, let's say, 3 treatment groups, treatment group number 1, 2, and maybe a control group. Describe how you're going to now randomly assign these 30 participants. The verbiage might be a little bit different. You're not sampling, but the concept is the same. So again, this is a kind of a high priority item as we look ahead into the AP exam, especially like for a FRQ question. Okay, must have, excuse me, must have skill number 3. This is slide number 10. I'm calling it the benefits of stratifying. Over the years, I've considered many AP questions, and it seems like one of the recurring themes is, do students truly understand not just the different sampling strategies? Like you're seeing if you look at the picture here, there's simple random sample, there's stratified random sample, cluster sampling, systematic sampling. I feel like you need to go beyond just understanding the differences. And one of the key benefit of stratifying is that it reduces variability. And I think you really should understand what that means and be willing to and be ready to answer questions about that. So first of all, strata. What's a strata? Strata are groups of individuals who share characteristics thought to be associated with the variables excuse me, being measured in a study. So in a stratified random sampling, you're selecting essentially a simple random sample within each stratum and then combining them into one overall sample. So for instance, in my classroom of, let's say, 27 students, and 14 of them are girls, 13 of them are guys, instead of saying, I'm going to randomly select, let's say, 5 people out of 27, I could first stratify the class by gender, let's say, into guys and girls, and then now randomly sample 2 guys. So there's a simple random sample of 2 guys and a simple random sample of 3 girls, and that combined gives me my total sample of size 5. You're like, well, why would you do that? Well, maybe I really want to, I think that there might be a difference. Maybe gender is going to play a role, right? Or maybe grade level will play a role. So that's the big idea. The big idea here is it's going to give you a more precise estimate than just selecting a simple random sample. It's going to kind of drown out the naturally occurring noise that can be accounted for by that variable that you just stratified by. In my case, it would have been gender. So the AP exam tip here is that you should understand the differences between the types of sampling method. And beyond that, understand the benefits of, let's say, stratified random sample. And I'm not going to click on this, but there's a pretty short YouTube video that I think does a really good job helping you visualize, what type of sampling is being described. So here's part C of this FRQ. Again, there's the stem. I'm not going to read that for you. Because stratification can often provide a more precise estimate than a simple random sample, the third method the administrator is considering consists of selecting a stratified random sample of 500 students. Now, the university has 2 campuses with male and female students at each campus. Under what circumstance or under what circumstances would stratification by campus provide a more precise estimate of the proportion of students who are satisfied with the appearance of the university buildings and grounds than stratifying by gender? So one thing that I'm seeing in people's responses is this idea that perhaps one campus is nicer than the other. That will certainly be a good reason to consider conducting or consider gathering a stratified random sample, a sample of students from this campus and a separate random sample of from the second campus to see if you believe that it's going to make a difference. And that's the idea. That's the absolute idea. So here's the model response. Stratified by campus would be more advantageous than stratified by gender, provided that opinions about the appearance of the university, buildings, and grounds between the two campuses differ more than the opinions about the appearance of university buildings and grounds between the two genders. In other words, there's got to be a compelling reason to believe that the opinions at one campus may be different than the other campus, more so than the differences that may exist between gender. So to get full credit, if I remember correctly, you do have to talk about how stratifying by campus is more advantageous than perhaps stratifying by gender. So take a quick breather here. Are there any questions about this overall FRQ? Something that you kind of have a burning issue with and I haven't addressed it yet.
I don't see it in the chat right now.
Okay, great. All right, so let's move on to must-have number 4. So let's move on to going from sampling to now really that's kind of the second half of this chapter, this unit. It's all about experiments. And boy, oh boy, there are tons of vocab when it comes to experiments, right? Explanatory variable, response variable, treatments, experimental units, subjects, control, placebo, randomization, replication, confounding, and the list kind of goes on. So I think one key component to success is to be really familiar with all of these vocabulary words. So I have 3 AP exam tips when it comes to experimentation. Number 1, when it comes to discussing variables, start by asking, and I think this might be a good tip for all of AP Stats, not just this chapter. When it comes to like variables, like data, I think we should all start by asking ourselves, is this quantitative? Is it categorical? Let's recap that real quick. Quantitative variables, it makes sense to talk about the average of that variable. Like age can be quantitative because you can compare, or you can compute an average age. Gender is definitely not quantitative. You can't talk about average gender. Gender is categorical. I mean, think about the word category. Yes, no answer, agree, disagree, somewhat agree. That categories, right? It makes no sense to compute the averages of. And I think that's important. As some of you guys are kind of starting to realize as we kind of head into the latter half of the, the study in AP Stats, it's all about, inference for quantitative data, inference for categorical data. So I think it kind of starts up here, right? Excuse me. Example number 2. You know the difference between observational study and an experiment. They're both studies, they're both statistical studies. what's the benefit of doing an experiment over say, a survey? And number 3, if you're asked to identify a confounding variable, kind of like the thing that we saw earlier about bias, there's kind of 2 components to it. So if you're ever asked to talk about confounding variable, you got to do 2 things. Number 1, you got to talk about how that potentially confounding variable is associated with the explanatory variable, the x variable, and how that confounding variable is linked with the response variable y. That's what makes it confounding. So let's take a look at another FRQ where each of these 3 items are hit. So here is, excuse me, FRQ from 2016. The stem of the problem is this: the Alzheimer's disease results in a loss of cognitive ability beyond what is expected with typical aging. A local newspaper published an article with the following headline: "Study finds strong association between smoking and Alzheimer's." The article reported that a study retracted a medical histories of 21,000 plus men and women over 23 years. The article stated that for those who smoked at least 2 packs of cigarettes a day, the risk of developing Alzheimer's disease was 2.57 times the risk for those who did not smoke. So on this screen, you were given parts A and B of this question. Part A says, identify the explanatory and response variables in the study. And part B asks you, is the study described in the article an observational study or an experiment? And explain. Once again, I'll give you guys a couple of minutes to think through this problem. Okay, so let's take a look at the model solutions. I think a lot of you guys did really well on these two parts. Now, this is one of the questions that I graded in 2016. It was my rookie year at AP Reading, and I got in trouble for apparently grading students a little bit too leniently because, for instance, I thought, okay, as long as students mention smoking as explanatory variable and Alzheimer's disease in the response variable, they should get full credit. Well, no, not quite. That's not enough. And you're like, why not? Take a look at the model solution for on slide number 15, part A. The explanatory variable is person's degree of cigarette smoking. So smoking by itself, it doesn't talk about how much, right? The person's degree of cigarette smoking or whether or not they smoke 2 packs a day. And the response variable is not simply Alzheimer's, which a lot of students wrote. The response variable here is, again, whether the person develops Alzheimer's disease. It's a categorical variable. Did they or did they not develop Alzheimer's disease? And explanatory variable, the way the question was phrased, to me, it sounds like it's a categorical variable. Did they or did they not smoke at least 2 packs of cigarette a day? So a special note here for you, describing the variables only as smoking and Alzheimer's without any reference to the status was not sufficient for full credit. So I would really encourage you guys to go back to your answer right now on slide number 14 and see how you did on part A. Would you ever receive full credit given the response that you typed in? Or do you think perhaps, oops, I was a little bit vague, unclear, and I might get at best a partial credit? Which, don't get me wrong, partial credit is credit, and it's going to help you, eventually pass the AP exam if you get enough of those partial credits. So the moral takeaway from part A is when you're asked to describe variables, again, think categorical or quantitative, which one is it? And then context. Context. And it's not just, I'm going to throw in a word here, a word there, full context. What exactly is it that you're measuring? If you're the researcher, what exactly is it that you are writing down on that spreadsheet or chart or whatever that you're using to collect data? Part B, I think it was unanimous. Nobody said it was an experiment, and you're right. This is an observational study. Why? Because people in the study were not assigned to a certain degree of cigarette smoking. Rather, the degree of cigarette smoking for each person was passively observed and recorded, not manipulated by the researcher. In other words, the treatment was not deliberately imposed. That's the textbook answer, right? There were no treatments involved. There were no treatments assigned. However, that answer, as popular as it was, if I remember correctly from 2016, that textbook answer got, I think, no more than partial credit. And in more recent years, that textbook answer gets no credit. Think back to this past school year in 2020 when the exam was done online. College Board was not going to give you any credit for essentially copying and pasting a textbook answer because it was an open resource test, right? So something for you to consider as we look ahead at the AP exam. So again, a special note here in the bottom of the screen, a simple statement such as, this is an observational study because treatments were not assigned. Not going to get essentially correct, probably not even going to get half credit. Okay, slide number 16. Here's part C of this question. So exercise status, regular weekly exercise versus no regular weekly exercise, was mentioned in this article as a possible confounding variable. Your job is to explain how exercise status could be a confounding variable in the study. So feel free to go back to slide number 13 to gather some hints on how to answer this question. So the common thing that I'm reading in your responses is you're making the link that perhaps people who exercise more regularly are more likely to not smoke as much. Okay, that's good. Just for mentioning that, you're making the link, the potential association between the confounding variable here, exercise, and the explanatory variable of smoking. Good, you're halfway there. What you also need to say is, okay, so how is exercise potentially linked to development of Alzheimer's? And I'm seeing a lot of that in your responses. So I'll be gut honest, this was a pain in the butt to grade in 2016. My rookie year, and oh my goodness, this was a pretty tough question to grade because we really had to read carefully of what the student was talking about. And I'm sharing this not because just about myself. I'm sharing this because I want you to take comfort in knowing that your responses to questions like this on the AP exam, it does get read, every single word. And if it doesn't quite make sense to the reader, we have a table partner, assuming that it's, we're there in person in Kansas City. And I'll turn to my table partner and say, hey, can you read this response? See what you think about this. Obviously, this school year, due to the pandemic, we're not going to be sitting at tables in Convention Hall in Kansas City. It's going to be done virtually. But even at that, I can quickly send a message to my table leader saying, hey, I have a question about this student's response. Can you please read it and give me some feedback? Long story short, your responses will be read, potentially by more than just one person, and it will be graded fairly according to the rubric. So it's all about satisfying the rubric. So in my opinion, your goal is, okay, what do I need to say to satisfy the rubric? So here's your model solution offered by the College Board that year. It is plausible that people who exercise more regularly might be more health conscious. Therefore, less likely to smoke cigarettes than people who do not exercise regularly. It is also plausible that people who exercise more regularly are also less likely to develop Alzheimer's disease than people who don't exercise regularly. And if both of these relationships are true, then smoking cigarettes would be associated with developing Alzheimer's disease due to the association of both variables with the exercise, even if there were no cause and effect relationship between smoking and Alzheimer's. Now that's a really, really full response. I think you can get away without omitting, some of the latter parts there. So if you're kind of like a little bit fuzzy about it, I would encourage you right now, I think this is 30 seconds well spent, to go back and forth between this model solution and your response on the previous slide and ask yourself, okay, is my response good enough for full credit, or would I have to settle for half credit here?
Dan, one point I wanted to make, if you don't mind, is that when readers look at responses, we are looking for quality rather than quantity. And we're not looking at your grammar. We're not looking at how words are spelled. We're looking at the quality of the response statistically.
Yes, absolutely. Thank you so much for chiming in. And we will do everything possible to read your handwriting, as difficult as that may be sometimes. Okay, guys, home stretch here. Slide number 18. This is your last must-have for this session. Similar concepts for different vocab. And you might think that this is pettiness, but it's not. Once upon a time, I thought it was petty too. Like, what's the difference? Stratifying and blocking, they mean the same thing. Well, no, not really. They don't mean the same thing. They have the same concept. Keep in mind that the idea of stratifying belongs in the sampling world. The same concept of stratifying, sorting your participants based on how they're alike. When you're doing an experimentation, you don't want to bring in the word stratifying. You want to use the word blocking. Concepts are the same, two different vocab. Keep those separate. Also, random selection belongs in the sampling world, where you're selecting people. Random assignment belongs in the experimental world. Same concept. Two different words, selection versus assignment. And number 3, understand the two different scopes of inference as possible based on whether your data are from a random sample or whether you are collecting data from a randomized an experiment that was done with a randomized assignment. And so this chart here, very similar to what's probably in many textbooks. Take a look at this. There's, let's just go through it real quick. So what's the benefit of gathering a random sample? Like, think back to that first FRQ that we looked at this morning. Why would the university be interested in collecting a random sample of 500 students from 70,000 students? Well, because if your sample was collected in a randomized fashion, in a random sampling scenario, then we can potentially generalize the results of that sample survey to the entire population of interest. In other words, random selection combats bias. So the estimate that we get from the sample would be what we call an unbiased estimator of the true population parameter at interest. Now, what's the benefit of random assignment? Cause and effect is this big, thing that we want to accomplish as statisticians, as researchers, and the only way to potentially establish a cause and effect relationship is to do a randomized controlled experiment. So those are two different scopes of inference. Can I generalize? The answer is yes, if your data are representative of the population of interest. Can I imply causation? Yes, potentially, if you did a randomized experiment, if you try to drown out the noise among your experimental participants. So let's take a look at, hopefully, several of these multiple choice questions. So here's multiple choice question number from 2012 here. Compact disc manufacturer wants to determine which of the two different cover designs for a newly released CD will generate more sales. The manufacturer chose 70 stores to sell the CD. 35 of these stores were randomly assigned to sell CDs with one of the cover designs, and the other 35 were assigned to sell the CDs with the other cover design. The manufacturer recorded the number of CDs sold at each of the stores and found a significant difference between the mean number of CDs sold for the two cover designs. So which of the following gives the conclusion that should be made based on the results and provides the best explanation for the conclusion? Okay, so 12 of you believe that the answer is, I didn't put the letters in, but that would have been D, the fourth one down, that it is reasonable indeed to conclude that the difference in sales was caused by the difference in cover designs, because the cover designs were randomly assigned to stores. And honestly, some of my students would have struggled with this. Like, Mr. Kim, like, you told us that establishing causation is like this really tough thing to do. I mean, it's virtually impossible, right? Well, not really. And the key word here is that 35 of these stores were randomly assigned to sell CDs. So because there was that random assignment involved, the answer is D. So good. Most of you guys got it right. It is reasonable to establish causation here. All right, let's take a look at another multiple choice question. Slide number 20. A randomized block design will be used in an experiment to compare two lotions that protect people from getting sunburned. Which of the following should guide the formation of the blocks? Okay, so we got a war here between choice B and choice D. Participants should be randomly assigned to the blocks. It sounds really good. Let me give you an example that I always offer my students when they choose this option. If we're doing a block design by, let's say, by gender, right? Can you flip a coin and say, hey, you've been randomly assigned to the girls block, and the guy is not a girl. So as silly as that may sound, that's kind of a giveaway. You can't randomly assign somebody to a predetermined block, by gender or by grade level. Like, here, you're a senior, but you've been randomly assigned to the freshman block. Can't do that. So it sounds really good, but unfortunately, that's not the right answer here. The correct answer is D. Participants within each block should be as similar as possible with respect to how easily they get sunburned. And again, so blocking is the same concept as stratifying, but it's just a different word that we use in an experimental situation. All right, I think we have time for maybe one or two more multiple choice questions. So go ahead, let's go on to slide number 21 here. The buyer for an electronics store wants to estimate the proportion of defective wireless game controllers in a shipment of 500 controllers from the store's primary supplier. The shipment consists of 200 boxes, each containing 25 controllers. The buyer numbers the boxes from 1 to 200 and randomly selects 6 numbers in that range. She then opens the 6 boxes with the corresponding numbers, examines all 25 controllers in each of those boxes, and determines the proportion of the 150 controllers that are defective. What type of sample is this? So this is a question where it's like, do you understand the differences, right, between all of these different types of sampling methods? You guys are on it today. Cluster sampling it is, absolutely. The key here is you randomly choose 6 boxes, clusters, and you're going to now examine everything inside that box. It's kind of like you walk, like in a school setting, for instance, homerooms. My school has homerooms. You randomly select 5 homerooms, visit those homerooms, and everybody in those 5 classrooms are in your sample. Okay, one more multiple choice question. We'll take a break. At a large conference of teachers from a variety of subjects, a random sample of 50 math teachers attending the conference was selected. Among the selected math teachers, 28% had taken 1 or more courses in stats. For which of the following populations is 28% a reasonable estimate of the percentage of those who have taken 1 or more courses in stats? Okay, so on this final question in this morning session here, once again, really good. All math teachers who attended the conference is the correct population of interest. So really, being precise about what you mean by population of interest, like it's all about from what, are you choosing that sample from, to what population of interest does a sample truly reflect. Okay, so guys, we're going to take about a 6-7 minute break right now. The last slide that I'll make available to you is just a little feedback, a little reflection. Feel free to do that for yourself. And we'll make a transition to another Desmos activity in approximately 6 or 7 minutes.
All right, thank you, Mr. Kim. We will start back at, let's see, we'll do 7 minutes. Well, let's do 8, and it'll be 11:10. 11:10. All right, Mr. Kim, we are back to you.
Hey guys, welcome back. Probability, here we go, woohoo! I dropped off the link to your next Desmos, and I will go ahead and share my screen as well. So either you can click on the link that I just dropped in the chat box, or you can go to student.desmos.com and type in ES3W3C. Calculator, paper, pencil will definitely be handy as you work out some math here. Now, speaking of AP stats not being very mathy, that is certainly the case for certain units. And then probability unit, definitely a little more mathy, I suppose, traditional definition of math. But my take on it is, I don't know if you guys will agree, the further we go in AP stats, like the second semester of AP stats especially, like between now and May especially, it's like English and math had a love child. Stats, you can call it stats. It's beautiful. All right, 15 of you guys are on so far. Give you guys about 30 more seconds to join this Desmos before we get going.
And I posted the code in the chat just in case you need it for reference.
Thank you. So I'll go ahead and give you guys access to slide number 2. Mainly for me, honestly, I just want to gather some opinions and thoughts from around the state, perhaps around the country. What's your view of probability? And you'll see that there's coordinate plane there. If you look at the scales, hopefully it'll make a lot of sense. And again, as you can see there, you're anonymized, so you can give your true sentiments here. I'm just kind of curious, like, because all I hear is, people that in my bubble, AKA my students. And if you would like, you can say a sentence or two about it, just for fun.
See an interesting perspective there. Probability is the opposite of how I think.
Yeah, I heard that. Yeah.
Yeah, exactly.
And you got Sophie Germain saying, hey, I like it. I think it's pretty straightforward. Kids have really hard time with it. Heck, adults have hard time with it, I think.
I think the gambling industry takes advantage of that.
Yeah, absolutely. The house always wins, y'all. House always wins. So what I'll do at this time is I'll show you the overlay, just kind of see like, okay, out of what, 19 of you, how do you all think here? We're all over the place, wow. For the most part, most of you guys are below the horizontal axis there. So you think that it's, to kind of hard. But there's one person who says it's really easy. Now this person's interesting here. Person's like, I love it, but it's so hard. All the way down to, man, I'm not a fan, and maybe because it's hard. I don't know. That's interesting, right? So, hey, look at that. Small sample size of you all, and there's already people everywhere. Great. You guys gave me a tough job to accomplish in the next 50 minutes, 45 minutes. Again, ask questions, please. If we don't get through all of these questions, it's okay. Let's focus on really digging into some of these questions. Okay, moving on to slide number 3. So this is Unit 4. Now the first half of the Unit 4, let me kind of expand this screen here. You can see that Unit 4 accounts for anywhere from 10 to 20% of AP exam. It's kind of vague, right? And we're going to hit 4.1 through 4.6 today. So really Chapter 5, if you will, for those of you who used the practice of statistics. And 4.7 through 4.12, that's like Chapter 6, if you will, in the same textbook. So we're going to address probability, the kind of the nuts and bolts of probability. We're not going to get into random variables and things like that. So here we go. I'm going to kind of take a similar approach here as the previous session. I want to just provide you some must-haves. Again, these are not all of them. 45 minutes is nowhere enough time to explore all the details. However, what are some nuts and bolts here? This is perhaps my 2 cents. You can take it or leave it. This is what I tell my students, especially the ones who dread probability. Keep it simple. Really, keep it simple. The big idea is that probability does not have to be like this complex, mathy, formula-driven unit. You know, notations and symbols. Like if you find yourself kind of like cringing, like I don't want to write capital P parentheses A, you know, upside down, all that stuff. Don't worry about it. You're not going to get penalized for not writing down proper probability notations. It's about knowing how to do it. It's about knowing how to calculate and interpreting it. So don't worry about the symbols. Just write down in English words the probability of, if you will. The key to success is to think in context. Don't say, like, okay, what formula do I use here? Think in context. Pay attention to important words like given, if, among, and, or. Those are, I think, top 5 key words when it comes to probability. And be comfortable working with fractions. I don't know what it is about high school students and their hatred towards fractions. I just don't get it. I think fractions are great, especially for this unit. So AP exam tip number 1 here, when asked to calculate probability from a two-way table, be sure to show your work. And what I mean by that is leave your answer as a fraction, not a decimal. Like 13 out of 52. You know, if you're using 2 values from the table, right? That's not only the correct answer, perhaps, that's not only an answer, you're actually telling the reader what values you're using from the table to get that answer. But if you did 13 divided by 52 and only put in the decimal version of that answer, you might get credit for the right answer, but you're not going to get credit for showing your thinking, your work. Tip number 2, the word or, as some of you guys may know already, I don't want to say always, often means to add. You're going to add some numbers together. The word and, not always, often means to multiply. This and this. You're going to probably multiply some numbers. And tip number 3, conditional probability is this thing that like people just kind of like dread over sometimes. My opinion is conditional probability is like playing Guess Who. I love playing this game. I don't know if you guys are familiar with this game called Guess Who. Basically, the idea is you ask question: does your person have red hair? Yes. Well, if the person has red hair, what do? You start knocking down everybody else who does not have red hair. That's exactly what conditional probability is. It's more information leads to a smaller sample space, if you will, smaller denominator, and that's going to increase your chance of correctly guessing the other person. Given, right? If. Given that the person does have red hair, okay, let's start eliminating some possibilities, increasing my chance. And I really couldn't find a good probability meme, so there you go. You get that guy instead. So there we go. Let's dig in. FRQ from 2011. The table below shows the political party registration by gender of all 500 registered voters in Franklin Township. Part A. Given that a randomly selected registered voter is a male, what is the probability that he is registered for Party Y? Okay, so there was no good way of fitting all of this without making it appear too small. So you have to scroll down a little bit. And if you're not familiar with Desmos, you can actually doodle on here. On this table at the very bottom, you got a pencil, line, eraser, and about 6 different colors there. So if you want to, you can kind of doodle on Desmos here, if you want to show, I guess, me your thinking, or if you just want to have fun with it. And I'll try to give you guys not as much time, maybe like 30 seconds or so, to answer questions like these. And I'm just going to showcase one of your work, if you don't mind. So, Herman Grassman, you're the first one on my list. So your answer is 48 out of 200, and it looks like you underlined the word or the row for male, and you circled the number 48. You circled the number 200. You're absolutely right. The answer is 48 out of 200. Notice that you didn't have to, I guess, like, convert that to decimal. Although if you did, I believe it comes out to 0.24, right? So this is conditional probability. It says given. So it's like, is your person a male? Yes. Okay, well, let's circle male's row. Let's essentially knock out the female's row. So there you go. The answer is 48 out of 200. And it's like, okay, so what exactly do I have to write down on my paper if this was the AP exam to get full credit? 48 out of 200. That's it. You don't need to write down a sentence. Like, this is a model response right here. Don't need to do all that. 48 out of 200. Done. And you're like, really? That seems minimalistic. The question didn't say explain. The question said, what is the probability? You just answered it. And you showed your thinking.
Goes back to that that quality, not quantity part.
Absolutely. Absolutely. Okay, here's part B of the question. Among the registered voters in Franklin Township, are the events is a male and is registered for Party Y independent? Justify your answer based on probabilities calculated from the table below. So I will give you more than 30 seconds for this one. I will give you a suggestion. You can use your answer in Part A to save a little time here on Part B. Okay, so I see that a lot of you guys are trying to compare two probabilities, and you're absolutely right. You cannot answer this question just by some hearsay, like subjectivity, like, well, no, they don't have to be independent because I'm not going to get you any points. I mean, you've got to compare two probabilities that are related. So let's take a look at some options here. On slide number 8, I'm giving you a couple different options. So one way to compare, first of all, the answer is no. The events are not independent. Like, there's some dependency here between being a male and being registered for Party Y. So one way is to use your answer from Part A, which was 0.24, right? In essence, you found the probability of registering for Party Y given that the person's male, 24% chance. So that's Y given male. You want to compare that to what's the overall probability of finding somebody who belongs to Party Y. That's 168 out of 500. So notice that this is where it's actually really helpful to convert your decimal or convert your answer into decimal so you can properly compare the two quantities. And because 0.24 is nowhere near 0.336, two events are not independent. It means that in this case, males are less likely, right? Registered for party Y, given that they're male. If we know that the person is a male, we're going to have a lower chance of finding somebody who belongs in party Y. That's one way to interpret it. In other words, these two events are dependent. Another option, and I think I saw a couple of you guys go this route. Okay, what's the overall probability of finding a male? Well, that's 40%, 200 out of 500. Okay, I want to compare that to what is the probability of finding a male just among party Yers, given that they register for party Y. That's 48 out of 168, if you look at the table. That's 0.286. Again, those two numbers are nowhere near the same. And I say nowhere near the same because, you know, if these numbers were like just off by a smidge, then I think you can argue like, you know, this is raw data from real life. One could potentially argue that perhaps gender doesn't play any role when it comes to party affiliation. So I think this is a must-have skill. Being able to answer questions like, are two events independent? And it's all about, again, conditional probability. It's an application of conditional probability.
All right. I don't think you answered this, but correct me if I'm wrong. But there's a question when asked about showing independence or lack thereof. Can you just find the probability of A times the probability of B and show that that is not equal to the probability of A and B?
I believe so, Dr. McGuffin. I think you have more experience than I do. I want to say that is legit. If you want to go down that route.
If I remember correctly, when we've scored questions like this in the past, then we have accepted that. But I wanted to clarify that, making sure that I was asking the question correctly there in the way it was written.
Yeah, I think so. I did not include that in my model solutions, but I believe that is okay. Yeah. And we'll take a look at that actually in a different example coming up later. Okay, here's part C. So part C says one way to display the data in a table is to use what is called a segmented bar graph. So maybe you remember this from way back in August or September. So the following segmented bar graph, constructed from the data in the party registration, Franklin Township table, shows party registration distributions for males and females in Franklin Township. Now, in Lawrence Township, the proportion of all registered voters for parties W, X, and Y are the same as for Franklin Township, and party registration is independent of gender. So that is not true in the Franklin Township. You can kind of see that visually in the segmented bar graph given to you, right? That gender does play a role. But what they're saying here is that in Lawrence Township, the proportion of all registered voters by parties is the same, but in Lawrence Township, the party registration is independent of gender. So in light of that, your job is to complete the graph below, showing the distributions of party registrations by gender in Lawrence Township. So you may have to use your mouse and try to doodle on the sketch tool. If you have a stylus and a touch screen, touch sensitive screen, that's a plus. But so I'm curious to see how you guys would choose to answer this question. Now, if you are stuck, I will showcase Sophie Germain's work here. This person definitely has something good going on. That's a good start. So a lot of my students, when I give them this question, they struggle with it. And so one hint that I offer them is say, okay, look at Franklin Township. There's a reason why the segmented bar charts don't look the same between gender, because gender does play a role. So what would it look like in general in Lawrence Township where gender doesn't play a role? And that kind of gets them to think about, like, okay, well, both of the segmented bar graphs, one for female, one for males, like, they should look identical. And you're absolutely right, they should look identical. So on top of that, we have to also address the fact that the proportions of registered voters stays the same as Franklin Township. And that's why I wanted to showcase Sophie Germain's work here. Notice that this person found essentially the marginal distribution by parties, right? Marginal distribution of parties, 80 out of 500, 244 out of 500, and so on. And so you would simply apply those proportions to both genders. And take a look at their work. Notice that person drew straight lines down for W, X, and Y, and that is absolutely right. So if you want to take a look at the model solution, here you go on slide number 10. Party W, party X, party Y, you find the proportions, and you apply it to both the females and the males. So I really like this question because it kind of circles back to this idea of independence way back to, Unit 1, Chapter 1. Graphically, what does it look like? If there truly is independence, what would the graph look like? And this is exactly what it would look like. I'll camp out just for a second here for you guys to take a look. All right, so slide number 11. Now, this was not officially part of the question, but I wanted to create another question. So here's part D. This is what I made up. Given that a randomly selected registered voter is a female, we're back to Franklin Township now, what is the probability that she is registered for party W or party Y? Okay, so I'm seeing a lot of 180 out of 300. Let's see if that's the right answer. Slide 12. And you'll be right. It's 180 out of 300, or 60%. So I wanted to just give you an example of how do you deal with the word or. The word, remember, or usually means to add. So it's party W or party Y. So any overarching questions from this first FRQ? If not, let's go ahead and move on to slide number 13. So when it comes to calculating probabilities, one of the things that we have to watch out for is asking ourselves, are we talking about independent events or dependent events in a sequence of events? So the big idea here is when a sequence of events are considered, we got to think about whether the consecutive events are independent, as in with replacement setting, or dependent, which often means without replacement. And I think AP exam tip number 1, I've already mentioned that already. And again, I just cannot emphasize this enough. Exam tip number 2, be sure to show your work. Even if it's just like simple mental math that you can do in your head or on the calculator, don't forget to write down your work so that you get the credit that you deserve. So take a look at this FRQ from 2014. So here's a STEM. There are 9 sales representatives, 6 men and 3 women. At a small company, wanted to send to a national convention. Now, there were only enough travel funds to send 3 people. So the manager selected 3 people to attend, and stated that the people were selected at random. The 3 people selected were all women. They're like, that's suspicious, right? So there were concerns that no men were selected to attend the convention. So here's part A. Calculate the probability that randomly selecting 3 people from a group of 6 men and 3 women will result in selecting 3 women. And ultimately, part B of the question says, based on your answer to part A, is there reason to doubt the manager's claim that indeed 3 people were selected at random? Okay, so I do want to showcase a common mistake that I'm noticing from several people, and I'm only doing this because I'm not trying to call you out or anything. So let's take a look at Simeon Poisson's response. Probably 3 women, 3 9th times 2 9th times 1 9th equals a 2 out of 243. The numbers that you're using for your numerator, absolutely right, because given that the first person chosen was a woman, you now have 2 women left. Now take a look at your denominator. Only the first 9 is correct. If you take somebody out, if you already picked a woman from the first round, right, now there are 8 people remaining, right? So it's now 2 out of 8. So you randomly select, let's say, another person, and that second person is also a woman. So now you have 1 woman remaining out of a total of 7 people. So this is what we call sampling without replacement. So these are dependent events. The probability that the second person chosen as a woman depends on what took place before. And probably that the third person chosen as also a woman depends on what took place before on the first and second trials. So I'll show you the model solution here on slide number 15. So the correct calculation is 3/9 times 2/8 times 1/7, which is 6 out of 504, which is about 0.012, about 1.2%. So again, quality over quantity, you do not have to show the probability notation. Like I noticed that some of you are trying to do that. You don't have to. What's going to give you full credit is 3/9 times 2/8 times 1/7 equals 6 out of 504. That's sufficient. Now what about part B? Part B, yeah, this is suspicious because the manager is claiming that, you know, they selected people at random, but if his claim is correct, there's only 1.2% chance, right, of selecting 3 women out of 9 when there were 6 men and 3 women. So this kind of raises suspicion, like, did manager really, you know, sample randomly here? And I love this question because guess what second half of AP Stats is really all about? Is this idea of statistical inference, making decisions, you know, guilty, not guilty, reject the null hypothesis, fail to reject the null. All of that relies on probability. And I'm saying this because I hope you guys will gain some motivation. Even though you may not like probability, it's the language that we speak to make statistical decisions. And this is a good example of it, without getting into the whole, you know, inferential vocabulary.
There was one comment about is not just probability, but here's what's come up and where it comes up quite often about rounding and recommendation on rounding. There is no specific rounding that is accepted or acceptable or not acceptable in AP statistics. That's different in other exams. In AP calculus, it's understood that you round to 3 decimal places, but AP statistics, there is no convention. So as far as a recommendation goes, that's really kind of up to you as a teacher. And Mr. Kim, do you have a recommendation that you use with your students?
I tend to say 3 or 4 decimals, just because it can make a difference. Now that's kind of vague because if you're using table A, for instance, you do have to round off the z-scores to the nearest, you know, 100th. So it kind of depends on context, but I agree with you. It's the importance is not precision of your answer, is showing your work and showing your thinking.
And so if you're telling your students round to 4 decimal places, then that's acceptable. And if you want to keep something consistent like that.
Yeah. All right, guys, take a look at part C of this question, slide number 16. So an alternative to calculating the exact probability is to conduct a simulation to estimate the probability. A proposed simulation method process is described below. So each trial in the simulation consists of rolling 3 fair 6-sided dice, 1 dice for each of the convention attendees. Now for each die, rolling a 1, 2, 3, or 4 would represent selecting a man. Rolling a 5 or 6 represents selecting a woman. And you do it 1,000 times. After 1,000 trials, the number of times a dice indicates selecting 3 women is recorded. The question is, does the proposed process correctly simulate the random selection process of 3 women from a group of 9 people consisting of 6 men and 3 women? Explain why or why not. Let's start thinking about this out loud here. Part of it sounds pretty good, right? There are 6 men and 3 women, so 2-to-1 ratio. And 1, 2, 3, 4 versus 5 and 6, that's a 2-to-1 ratio. So the setup looks legit, and it is for the first person, right? So if you roll that first die, that correctly simulates the chance process here of choosing between, 6 women and 3 women, 6 men and 3 women. However, for the second and the third dice, it's not correct. And this has to go back to the idea of, okay, are these dependent events or independent events? Since you guys are just probably stepping out of random variables unit, perhaps, this is a question of, is this a binomial setting or is it not? Is the probability of success staying constant? And it doesn't. Because again, if you select somebody, whether it be man or woman, there are no longer 9 people available to choose from. Now there's 8. And the number just keeps on going down after that. So the answer is no. So your reasoning is what's going to get you the point here. So here's the model solution. And I saw some of this on your responses. That's really awesome. The process does not correctly simulate the random selection of 3 women from a group of 9 because the random selection of 3 people among 9 is done without replacement. However, the simulation with the dice, the 3 dice rolls in any given trials are independent of one another, indicating a selection process that is done with replacement. So deeper understanding of this situation right here, I think, will help you understand at a deeper level what it means to truly evaluate binomial versus non-binomial setting. And ultimately, when you get into like sampling distribution, the concept of why do we have to check the 10% condition? And what is the condition all about? And it's all about this. So that's not the topic of this review session, so I'm not going to go into it. But if you want to stick around, I'd be happy to chime in further on that concept. Okay, must-have number 3. So mutually exclusive versus independent. So I've kind of solicited some feedback from some teachers as I prepare for this session. And one of the things was, students tend to really struggle with this idea between mutually exclusive events and independent events. So I have some illustrations here. As Dr. McGuffin pointed out earlier, if 2 events A and B are truly independent, then the probability of A and B can be found by doing probability of A times probability of B without worrying about any, givens. Mutually exclusive events is about finding probability of A or B, and if events A and B are mutually exclusive, then the probability of A or B is purely probability of A plus the probability of B. You don't have to worry about the overlap. So these 2 formulas down here, and I know I'm kind of going against what I just said, but if you're a formula-driven person, these are the only 2 formulas that appear on that AP formula table reference sheet that you'll be given for the exam. You're like, gee, that's it? That's all I'm going to get? And honestly, if you think about it, that's really all you need when it comes to probability. The top one here, that's conditional probability. You can kind of rearrange that to make it into what we call the multiplication rule. And the one that down here, the probability of A or B, that's what we call the general addition rule, right? And if A and B are mutually exclusive, probability of A and B is 0 because they can't happen at the same time. So let's see how this kind of plays a role on our next question. So here's a multiple choice question. The SC Electric Company has bid on 2 electrical wiring jobs. The owner of the company believes that the probability of being awarded the first job, we'll call that event A, is 0.75. The probability of being awarded the second job, we'll call that event B, is 0.5. And the probability of being awarded both jobs, so we'll call that event A and B, is 0.375. If the owner's beliefs are correct, which of the following statements must be true concerning events A and B? Concerning events A and event B. Okay, so 12 people believe that the answer is C, that events A and B are not mutually exclusive. That's correct. How do we know that? Because events A and B happening together is 0.375, right there. We know that it can happen together. Now, how do we know that they're independent? Well, they're independent. Here, I'll show you slide number 20 here. Oh, sorry. My fault. Don't go to slide 20 yet. I thought that was the answer key. No, they're independent because if you go back to slide number 18, probability of A and B, if they're independent, we can see if probability of A times the probability of B is equal to probability of A and B. And back to slide number 19 here. If you do 0.75 times 0.5, guess what you get? You get 0.375. So numbers work out. Events A and B are independent. Absolutely. Okay, so let's take a look at slide number 20. This is, I believe, the last must-have that we have time to address. Tree diagram. And you're like, oh my gosh, like I hated this. I don't know, maybe you like it, but for whatever reason, my students are not a fan, even though it's so helpful. So I have an illustration up here just to kind of demonstrate what a tree diagram, again, looks like. Now, what's the big idea? When is it helpful? A tree diagram can be really useful to organize and show all possible outcomes of a random process that involves stages, like first this, then this. I think it's really, really useful. Rarely, if never, on the AP test, will directly say, draw a tree diagram. It's not going to say that. So you have to kind of determine, like, do I want to use this? Do I need to use this? And, that's kind of the thing that you have to play. So I think we have time to do, hopefully, this multiple choice question. So if you have paper handy, I think it might be, I don't know if, actually, I think I included doodling. Yeah, so you can either do it on here or on paper. I don't care. So here's a question. 90% of the people who have a particular disease will have a positive result on a given diagnostic test. 90% of the people who do not have the disease will have a negative result on this test. If 5% of certain population has a disease, what percent of the population would test positive for the disease? So what's the overall positivity rate given the numbers that we have here? So if you're totally, like, I don't even know how to get this problem started, consider drawing a tree diagram. Consider drawing a tree diagram. First, I will split it off at the beginning, and I'm kind of doing it on my screen as well. So either the person has the disease, okay? Like, this is like, what's the truth? Do they have the disease or do they not have the disease? I'll just call it not. Please excuse my terrible handwriting there. So you got to start there. So based on whether they have or don't have the disease, now the question is, the second stage is, okay, did it yield a positive result or a negative result? And in a medical setting, one of this is called a false positive, and one of this is called a false negative. But that's not the thing that we're addressing here. What we want to address in this question is, what's the overall positivity rate? So once you find those values, you have to add them together. Yes, I'm starting to see a lot of success here. And one thing that I will quickly comment is, do you have to draw a tree diagram to successfully do this question? The answer is absolutely no. Now I'm looking at, Victor, Newman, Laura here. I don't know, maybe the person did their work on paper, but the work that they showed on the screen, I know it's really small. They're simply doing 0.05 times 0.9 plus 0.95 times 0.1 gives you 0.14. So tree diagram is a tool. You can choose to use it if it helps you organize the branches, the possibilities. But if you can kind of do that in your own head, like here are the things that I want to count, no, you don't have to draw a tree diagram. So the correct answer here is indeed 14%. And I'll show you the work that I prepared ahead of time on slide number 22 there. And I think we may have time to do our very last question, unless you have any questions here. Okay, so let's take a look at slide number 23. Last question, guys. So the distribution of colors of candies in a bag is as follows. So you guys see here, there's brown, red, yellow, green, and orange. Now this is called a probability distribution. Let's just kind of camp out here for just a second. A couple things that you need to know for probability distribution. First of all, what is it? List of all the possibilities along with their corresponding probabilities. So here we got list of all the possible colors of candies along with their corresponding probabilities. That's the definition. What should you know about it? The probabilities must add up to 1. That's an absolute rule for it to be a legitimate probability distribution. And if you kind of look at the numbers here, they do indeed add up to 1. And again, in a random variables unit, that becomes really handy for discrete random variable. So the question is, if 2 candies are randomly drawn from the bag with replacement, what is the probability that they are the same color? So it's unanimous. For those of you who've answered the question, you are saying that it's 0.22, and you are absolutely right. And so here is a model solution here. So probably the same color. There's 5 different ways to achieve that, right? Brown and then brown again, red and red again. And the key word here is or. Brown and brown, or red and red, or yellow and yellow, and so on. So the fact that you're going to put this candy bag into the bag means that all the probabilities stay the same. So these are independent events. Every time you draw in, you're going to have the same chance of picking red, brown, yellow, green, and orange. So absolutely right. 0.22. So guys, that is it from me today. Again, the last slide is for you to just do some reflection of what you may need to work on. These Desmos activities, both of them, you can access them again at any time. So I would encourage you to do so. And if you have any questions, please don't hesitate to either reach out to me directly. My email is available to you on the, I think, front of the screen. But guys, thank you so much. What a great way to spend Saturday morning reviewing almost 20 to 25% of AP stats. Thank you for your investment this morning.
Just to wrap things up here, there will be a recording of today's session. That's at bit.ly advanced KY with make sure that's capital A and capital Y. And if you have any questions, you can contact me, Dr. Sherry McGuffin, smcguffin@kstc.com. Follow me on Twitter at Dr. McGuffin. Erin Timmons is our content director for mathematics at Advanced Kentucky, and A. Timmons at kstc.com, and our ARTIMM2 on Twitter. And then you can reach out to Mr. Kim at Louisville Middle High School, daniel.kim@jefferson.kwestcoast.us. Thanks for attending today. And if you have any questions, you're more than welcome to out with us after we complete the session and stop. And hopefully we will see you again soon. Come visit. Next session's March 13th, random variables, probability distributions, and sampling distributions. And that's with Kelly Lee of Glasgow High School. Thank you so much.